Welcome to the final lesson of the course. So today we conclude with gamma convergence, and in the first part of the lecture, I would like to talk about the fundamental theorem of gamma convergence, which basically ensures that basically shows that if you have a sequence fn which gamma converges to a limit functional f, then we will prove that the minimum problems for Fn converge to the minimum problem for F, roughly speaking. And also that, again, roughly speaking, that the argmin of Fn converges to the argmin of F. Okay, in order to prove this result, we start with this technical lemma. So let Xd be a metric space, Fn be a sequence of functionals from X into the extended reals, and Fn a sequence, and assume that Fn gamma converges to some limit functional F. Then the conclusion is that the gamma limit is lower semi-continuous. So proof, assume that Xn goes to X0, we need to show the lim-inf inequality, so the lower semi-continuity inequality. Now, since Fk gamma converges to F, so here I'm just changing the letter for the natural number here, so this doesn't matter. Since Fk gamma converges to F, then for each Xn fixed, Xn being one of these points, there exists a recovery sequence which we denote by Yk, such that it does what a recovery sequence does. So Yk converges to Xn, Sk goes to plus infinity, and then the energies, so Fk of Yk converges to the limit energy f of Xn, Sk that goes to plus infinity. Therefore, by this condition, and which holds for every n fixed, and by a diagonal argument, we can find a sequence which we call yn tilde, such that star holds. And star says that the distance from yn to xn is less than 1 over n. And this is clear because this one holds. So you, by a diagonal argument, you can select such y tilde n. And also the other condition is that Fn of y tilde n is close to f of xn for every n. And again, this is easily obtained by this condition here. Now, recall that we were assuming xn converging to x. Therefore, the first condition, since y1 over n is going to 0, by triangle inequality, you infer that yn tilde goes to 0, goes to x. And therefore, we obtain that f of x is less or equal than the lim-inf of fn of yn, and this is by the gamma lim-inf inequality, because yn is converging to x, and therefore, by the gamma lim-inf inequality, this has to hold. Now, for the second inequality here, we use this condition. So we know that fn of yn is less than f of xn plus 1 over n, and so also the lim-inf is less or equal than the lim-inf of f of xn plus 1 over n. And now, since 1 over n goes to 0 by the property of lim-inf, this is just equal to the lim-inf of f of xn. And this shows, so lim-inf f of xn larger or equal than f of x, meaning that f is lower semi-continuous because xn was an arbitrary sequence converging to x. Okay, so this concludes the proof. Okay, a second technical result is given by proposition 11.9. So let Xd be a metric space, Fn be a sequence of functionals, such that Fn gamma converges to some limit functional f. Then we have these properties of the limit problems, of the, infimum problems. So we look at the infimum for x in A and the infimum for x in K for the functionals Fn. And we want to see, want to estimate this in terms of the infimum over the same sets of the gamma limit. So point 1 says that if A is an open subset of X, then the lim sup of the infimums over A is less or equal than the infimum over A of the gamma limit. Point 2 instead tells you that if K contained in X is compact, then the lim-inf of the infimums for X in K of the functions Fn is larger or equal than the infimum over K of the gamma limit. So let's see the proof of this proposition. Point 1, fix epsilon positive. By definition of infimum, you know that you can find a point X in the open set A such that, I mean, in the set A, it doesn't matter that it's open. It's important that it's not empty. So you can find a point such that f of x hat is less or equal than the infimum of f of x over A plus epsilon. Now consider a recovery sequence for this point x hat, meaning that xn, so a recovery sequence will be such that xn converges to x hat, and also the gamma limit evaluated at x hat has to be larger or equal than the lim sup of fn of xn. Okay, now since A is open, X belongs to A, and you have this convergence here, then it means that Xn must belong to A for n sufficiently large. And therefore we obtain the following estimate. So the infimum of X over A for X in A, sorry, of f of x plus epsilon, this is larger or equal than f of x hat because of star. So this was just the definition of infimum. Now, since xn is a recovery sequence for x hat, we have that this is larger or equal than this lim sup. And now remember that xn belongs to A for n sufficiently large, meaning that you can just estimate fn of xn with just the infimum of fn over the set A, because again xn belongs to A if n is sufficiently large. And therefore, this property, so this estimate here, holds also for the lim sup. So I can just take the lim sup on the left-hand side and the right-hand side, and in the end find that this quantity is larger or equal than this quantity here. And since epsilon is arbitrary, we conclude that the lim sup of the infimums is less or equal than the infimum of the gamma limit, as claimed. So let's see the proof of point 2. Consider a sequence xn in the compact set K of quasi-minimizers. So by quasi-minimizers, we mean basically an infimizing sequence for, infimizing sequence, but for the whole, basically uniform for these problems here. Okay, and you can always find such sequence with a diagonal argument. So the quasi-minimizers satisfy fn of xn less or equal than the infimum over k of the functional fn plus 1 over n, and this is satisfied for every n in n. I mean, apologies, you don't even need a diagonal argument. I mean, this is just choose epsilon equals 1 over n, and you can find such xn satisfying this estimate for every n. Now, since X is compact, K is compact, sorry, and Xn is contained in K, it means that up to exacting a subsequence, which we don't reliable, we can assume that Xn converges to X hat for some X hat in K. And therefore, we have the final estimate. So, infimum of f of x over K, this is obviously less or equal than f of x hat, because x hat belongs to K. And this by the gamma lim-inf inequality, since xn converges to x hat, this is less or equal than the lim-inf as n that goes to plus infinity of fn of xn. And this by double star, which is here. So pointwise, this guy is less or equal than this guy, as is written here, for every n, and therefore this is true also for the lim-inf. Meaning that the lim-inf of this guy is less or equal than the lim-inf of this. And then now, as usual, since 1 over n converges to 0, by the property of lim-inf, we conclude that this is just equal to the lim-inf of the first part. So you obtain this quantity here, proving that the inf over the compact set is less or equal than the lim-infs of the infimums on the compact set of the sequence. And this concludes the proof of this technical proposition. Okay, so now before stating the main theorem of the day, we need a definition, the definition of equicursivity. So remember that a functional, we define a functional to be coercive. So we did this a few lessons ago. So this is coercive if there exists K containing X compact. So K has to be compact, such that the infimum over K of F is equal to the infimum over the whole space of F. And now we just require equicursivity. We just require this condition to hold uniformly for a sequence of functionals. So let Xd be a metric space, Fn be a sequence of functionals. We say that Fn is equicoercive if there exists a subset K of X, which is non-empty and compact, and such that the infimum of Fn for X in X is equal to the infimum of Fn for X in K, and this has to be true for every n in n. So the only difference with the other sequence, the only difference with the coercivity definition is that we are not only requiring that Fn is coercive, so each single function is coercive, but that they are coercive on the same compact set. So because we're requiring this condition to hold with the same set K here. So K does not depend on n. So this is the difference. Okay, we have this remark that could be useful to check equicursivity. Let Xd be metric, Fn be a sequence of functions, and suppose that there exists a constant m in R such that this set here, so this common sublevel, so these are the point x in X, such that all the functions are less or equal than m for every n. So Fn of X is less or equal than n for every n in n. So assume that this set here, this common sublevel, is non-empty and pre-compact. Then it is possible to show that Fn is equicoercive. And the proof is actually obvious because it is sufficient to set K, just take the closure of this set here, so which is what I wrote here. This is non-empty, clearly, because this set here was non-empty. It is compact because we assume that this guy here was pre-compact, so its closure is obviously compact by definition. And you can check by hand that that this set here satisfies the condition of equicursivity. So the inf over of Fn over the space X is equal to the inf of Fn over K, and this is true for all n in n. Okay, so this is just to tell you that if you want to check equicursivity, this is a stronger condition, and maybe it is easier to check than this strange condition here with the infimums. Okay, so now we're ready to state and prove the main theorem of this lesson, and probably the fundamental theorem of gamma convergence. So let Xd be a metric space and Fn be a sequence of functionals. And we make only two assumptions. So first, we suppose that the sequence Fn is equicoercive with respect to some compact set K. And two, we suppose that Fn gamma converges to some gamma limit F. Okay, so this is our usual situation. We have a sequence of functionals, and we prove that they gamma converge to something, and also we prove that they are equicoercive. Then, if we have that 1 and 2 hold, we have also the following. Number one, the gamma limit admits a minimum on x. So the gamma limit actually is minimized by something, which is not trivial, I would say. Then number two, as n goes to plus infinity, we have that the infimum problems for the sequence of functions converge to the infimum problem for the gamma limit. So minimum infimums are converging to infimums. And actually the infimum for the gamma limit is a minimum because of 0.1. Number three, this says something on the on the almost minimizers or sequences of minimizers, I mean. So assume that Xn is a sequence of almost minimizers, meaning that the energy of Fn of Xn is asymptotic to the energy of the infimums. And this is encoded in the fact that if you take the limit as n goes to plus infinity of Fn of Xn minus the infimums, this has to be zero. So if Xn is such sequence, and we also assume that for some subsequence x and k is converging to x hat, then x hat is a minimum for f over x. Okay, so 1 second to summarize. This one is telling you that the gamma limit always admits a minimum. The second one is telling you that gamma convergence is stable with respect to infimum problems, which is precisely the point why gamma convergence was introduced, actually. Telling you that the infimum problems converge to the limit problem. And number three, it also tells you that if you take a sequences of almost minimizers, such that they are pre-compact, then the limit points are minimums of the gamma limit f. So let's prove this theorem. We start by showing that f, the gamma limit, admits a minimum over the whole space X. So first of all, remember that in lemma 11.8, we proved that any gamma limit is actually lower semi-continuous. So f is lower semi-continuous. Then remember that we assumed that the k, so this k, set k was the set of equicursivity. So we assume obviously that the set k is compact. And therefore, by the direct method, f is lower semi-continuous on a compact set. And therefore, if we restrict our function f over k, we have that there exists a minimum of f over k. So this is the direct method in the version of theorem 9.4. So we call x hat in k this minimizer for the gamma limit. Now the claim is that this minimizer x hat is actually a minimizer over the whole space X. So and now we're going to prove this fact. So to prove that fx is actually fx hat is actually a minimizer over the whole space, we just fix y in x arbitrary, and then we need to show that f of y is larger or equal than f of x hat. Okay, this would show that x hat is a minimizer over the whole space. So for this point, arbitrary, there exists a recovery sequence yn, because remember that we were assuming that fn gamma converges to f. So let yn be a recovery sequence for y, meaning that yn converges to y, and f of y is equal to the limit as n goes to plus infinity of fn of yn. And yeah, I mean, remember that this can be taken as a limit because of a remark we made just after the definition of gamma convergence. So then we have that f of y, this is equal to, by this condition, is equal to the limit of the energies computed on yn. Now you know that this sequence here is convergent, obviously, it's written here. And so this limit is equal to the lim-inf. Now, by definition of infimum, yn is an element of x, so fn of yn is larger or equal than the infimum of f of n, fn, sorry, over the whole space. And this is true for every n in n, and therefore it's true also for the lim-infs. So this is just the definition of infimum. And now here we can use equicursivity. Equicursivity tells us that for every n fixed, the infimum for x in x of fn of x is equal to the infimum over k of the functionals. So this is a strong point. I mean, this equality would not be trivial at all if we, I mean, it would be false in general if we don't assume equicursivity, of course. And so this liminf is equal to this liminf here, because again, this is true for every n in n by equicursivity. And now we can use proposition 11.9.2, which tells us that the liminf, since k is compact, so let's write this, k compact. So now, since k is compact, by proposition 11.9.2, we know that the liminf of the sequence of infimums over the compact set k is larger or equal than the inf of the gamma limit over the same set. And this is equal to f of x hat by k. K was this condition here. K told you that the minimum, so the infimum, which is actually a minimum, is achieved by x hat for the gamma limit. And therefore, if you just look at right-hand side and left-hand side, we prove that f of y is, for example, larger or equal than f of x hat. And since y was arbitrary, we conclude star. So we conclude that we conclude that x hat is actually a minimum of the gamma limit over the whole space X. Okay, point 2, we want to show that that the infimums for the problems converge to the minimum of the gamma limit as n goes to plus infinity. So we start with this inequality. The infimum of f of x. So here we want to use proposition 11.9.1. Remember that this proposition told you that this infimum is larger or equal than the lim sup as n goes to plus infinity of the infimum x in x of fn of x. And this is true. So proposition 11.9.1 tells you that the infimum is larger or equal than this quantity, and this can be applied with x because x is open by the very definition of open set, and and therefore the infimum of f of x over the whole space is larger or equal than the lim sups, and the lim sup is larger or equal than the lim inf, and so we obtain this inequality here. Now here again we use the equicursivity. So for every n in n, this is true. So the infimum of fn over k is equal to the infimum of fn over x. And so it is true also for the lim-infs. And now here we want to use again proposition 11.9, but point 2 this time, which tells you that if, since we are on a compact set, then this lim-inf is larger or equal than the infimum for x in k of the gamma limit. And now this is equal to the minimum of the gamma limit over the whole space, because we just proved this in point 1. So in point 1 we showed that we basically showed that, so since k is compact and f is lower semi-continuous, then there exists a minimizer, sorry, in k, and then we proved that actually this minimizer is a minimizer over the whole space, and in particular this follows. Okay, so this shows that the lim-inf for these problems here is equal to the minimum of the gamma limit over the whole space, because I mean we just showed that this is yeah, sorry, I got a bit confused. Sorry, this guy is equal to this guy again by since f admits a minimizer by point 1. So it means that everything inside this inequality is equal. So this is equal to this one in particular. So in particular, we just proved that the lim-inf of the infimum problems is equal to the minimum of the gamma limit. And now we just need to prove the other inequality, or the other condition, that the lim sup is less or equal than this lim inf, for example. So to do that, let x hat be a minimizer for f on x, which exists by point 1, and let xn be a recovery sequence for x hat, meaning that xn converges to x hat and the energies converge to the right thing. So clearly you have that, I mean, this is trivial, you have that the infimum of fn over the whole space is less or equal than fn evaluated on this recovery sequence for every n in n, since this is just an arbitrary point. So if we take the supremum in the above inequality, just take the lim sup here and the lim sup here, and you obtain that lim sup of this is less or equal than lim sup of this one, and is equal to f of x by definition of recovery sequence, f of x hat, sorry, and f of x hat is equal to the minimum of f of x, because we chose x hat to be a minimizer of f. And so in total we prove that the lim sup of the infimum problems is less or equal than this minimum. But then we are done, because we have three triple star here and double star, which if we put them together, just to summarize things, actually the thesis now is trivial, but this is just to summarize. So the minimum of the gamma limit over the whole space by double star is equal to the lim inf of the infimums. Obviously lim inf is less or equal than lim sup by obvious properties of lim inf and lim sup, and this last inequality instead is by 3. And so this shows that lim inf is equal to lim sup, and it's equal to the minimum, concluding that inf x in x fn is converging to the minimum x in x of f, which was the thesis of point 2. Finally, we're left with with point 3. This is trivial. So let xn be a sequence of quasi-minimizers such that x and k converges to x hat. Then we have the following. So x and k converges to x hat means that the energy of x hat for the gamma limit is less or equal than the lim inf of f and k, x and k. This is just the gamma lim inf inequality, and we're using that fn gamma converges to f. And now by adding and subtracting, we just add and subtract this guy here. So this lim inf is equal to this guy, obviously. And this first term here goes to 0. So the limit as k that goes to plus infinity of this guy goes to 0, because we're assuming that xn, sorry, is a sequence of quasi-minimizers. So by definition, this one goes to 0 as k that goes to plus infinity. And therefore, by the property of lim inf, this is just equal to the lim inf as k that goes to plus infinity of this term here. And this, by point 2 of this theorem, we know that this guy here, the whole sequence actually converges to the minimum problem for the gamma limit. So in particular, the lim inf also converges. And this shows that x hat, so this shows, sorry, that f of x hat is less or equal than the minimum, meaning that x hat is actually a minimizer for f over x, proving that limit points of quasi-minimizers are minimizers of the gamma limit. And this concludes the proof of the fundamental theorem of gamma convergence. Okay, in the rest of the lesson, I won't give any more abstract results, but I just want to focus on a couple of examples, and basically finish the course with these two examples. Okay, so consider this function here. Pardon. So fn of u is defined on C1 functions, and it is just the integral from 0 to 1 of n times u dot squared plus u minus the arctan of x all to the power of 2. So the question is, what is the limit of the infimum problems? So define Mn to be the infimum of Fn of u for u in C1 of 0, 1. And the question is, can we compute this limit? And so obviously the idea is to apply the previous theorem 11.12. And so we need to show two things. Number one, we need to show that Fn gamma converges to some functional f. And number two, we need to show that Fn is equicoercive. If we prove these two things, then we conclude that Mn, which is the inf of Fn, actually converges to the minimum of f, which is the gamma limit. And so we find a limit for this sequence of infimum problems. So to prove gamma convergence, first of all, we have to put ourselves in a decent ambient space. So in the decent ambient space, which contains C1, is obviously L2 of 0, 1. So we just extend Fn to plus infinity in L2 minus C1. So if u is only L2 but not C1, we set Fn of u to be plus infinity. And notice that this obviously does not alter this quantity here, because I mean the infimum, the infimum, I mean, yeah, because we're just setting the functional to be plus infinity on everything which is not in C1, and therefore this infimum, unless it is plus infinity, it is going to be smaller than the infimum over L2. Okay. So, okay, first we extend, and now the claim is that Fn gamma converges in L2 of 0, 1 to some functional f, where the functional f is defined in the following way. So it is the integral from 0 to 1 of u minus arctan of x, all squared, if u is constant, and plus infinity otherwise in L2 of 0, 1. So okay, let's see why this is a decent guess for the gamma limit. So first of all, by the stability properties, we saw that if you have Fn plus g, then this gamma converges to f plus g if Fn gamma converges to f. So this was a stability property that we proved. Therefore, since this term here, I mean with the integral of course, is continuous in L2, we just need to look for the gamma convergence of this guy here. And now imagine you're just sending n to plus infinity, and the reasonable thing for the gamma limit to do is to basically minimize the energy, because that's what not minimize the energy, but capture the asymptotic behavior of minimizers. So the only reasonable thing to do to be below all these problems here, all the infimum problems for Fn of u. So in the sense that, because you need to have this inequality, right? Liminf and Fn of u. So the only reasonable thing, Fn of un, sorry, on any sequence un converging to u. The only reasonable thing would be that this guy in the limit disappears. And this disappears in the limit only if u dot is equal to 0, meaning u dot is equal to a constant. So that's why this guess for the gamma limit. We are just saying that integral of 0 to 1 n u dot squared gamma converges to 0 if u constant and plus infinity otherwise. Okay, now let's see this in more precisely. So proof of claim. As I was saying, notice that Fn can be written as Gn plus h, with Gn, this guy here. So it's just the integral of the first part, if u is in C1 and plus infinity otherwise, and h is the second term appearing in the definition of Fn. Clearly h is continuous in L2, and therefore by proposition 11.4, the one on stability, it is sufficient to compute the gamma limit of Gn. So we have that, so we claim that rather, that Gn converges to G, gamma converges to G, where G is defined to be 0 if U is constant, and plus infinity otherwise in L2 of 0, 1. So G, capital G is just the gamma limit of, of this guy here. Okay, let's prove this, this claim, starting with the gamma limit inequality. So we suppose that UN converges to U strongly in L2 of 0, 1, and we need to show the limit inequality. So G of U is less or equal than these limits. As usual, without loss of generality, you can assume that this guy here is finite, meaning that there exists a subsequence such that G and K of U and K is less or equal than M for some constant M, and this is true for the whole sequence. So by definition of G, this means that, by definition of Gn, this means that, first of all, it means that UN belongs to C1 and UNK, sorry. And second of all, it means that the derivative is less or equal than M over NK, because remember Gn of UN, if UN is C1, this is just equal to this guy here, UN. Okay, but then this is telling you that UNK is converging to 0 strongly in L2 of 0, 1. So because NK tends to plus infinity as K goes to plus infinity, being this one a subsequence. Okay, since we're assuming also that UN converges to U strongly in L2 of 0, 1, so you have these two facts here. UNK converges to U strongly, and UNK dot converges to 0 strongly. Therefore, we can just apply remark 7.17, which tells you that if you have strong convergence in L2 of the functions and strong convergence of the derivatives, weak derivatives, sorry, then you have convergence in W12. So this is telling you that U and K converges to U strongly in W12, and also that U dot is equal to Z, exactly that the weak limit of this guy is equal to 0. So U dot is equal to 0 weakly. And now, this in particular, this is telling you that U belongs to W12 of 0, 1, because you have strong convergence in W12, and so U dot belongs to W12. And also it's telling you that U dot, the weak derivative, is continuous, because it is equal to the constant function 0. And therefore, in particular, U belongs to C1 by proposition 7.22, which was telling you that if U is a Sobolev function with a continuous weak derivative, then the function is itself C1. And in particular, this relationship here, U dot equals to 0 weakly, also holds in the classical sense. And so this means that if, in particular, since U belongs to C1 and U dot is 0, then it means that U dot is constant, because 0, 1 is simply connected. And therefore, G of U is, by definition, since U is constant, then G of U is equal to 0, and the gamma limit inequality trivially holds, because Gn is larger or equal than 0. So this is the gamma limit inequality. We prove that whenever you assume this one, if this is non-trivial, so if this right-hand side is less than plus infinity, then we prove that the limit U is actually 0. So we prove that U is actually constant. And then we know that G of a constant is equal to 0. And so we just need to prove that the limit is larger or equal than 0. But by definition, these functionals are non-negative. And so this follows. Okay, Gamma-Lin sup inequality. Let U in L1 of 0, 1, we need to construct a recovery sequence. So if U is not constant, so now we do all the cases. If U is not constant, then by definition G of U is equal to plus infinity. Therefore, just take the constant recovery sequence, and so that obviously you have that un converges to u in L2. And also trivially, you have the lim sup of gn of un, whatever it is, it must be less or equal than plus infinity, which is equal to g of u. So basically, this is telling you that if u is not constant, then the a constant recovery sequence does the trick. So it is a recovery sequence. If instead u is constant, then we know by definition that g of u is equal to 0. Again, take the constant sequence. Then obviously you have that un converges to u in L2. And moreover, since u is constant, then in particular u belongs to infinity, and u dot is equal to 0. Okay, why am I saying these obvious things? Yeah, sorry, because a priori u only belongs to 2, to L2. And so in particular, if I'm telling you that u is also constant, then u is smooth, and also u dot is equal to 0. And therefore you have that, you can compute the energy, you have that g of u, gn of un, this is equal to gn of u, because of how we selected the recovery sequence. And now, since u is actually smooth, this is by definition equal to the integral from 0 to 1 of n times u dot squared. And now u is constant, so u dot is 0, and so this is equal to 0. And this is equal to 0 for every n in n, meaning that the gamma-Lin sup inequality trivially holds, because, I mean, g of un is equal to 0, which is equal to g of u by assumption. Okay, so this shows that Gn gamma converges to G, and therefore since we already noticed that Fn is equal to Gn plus H, and H is continuous, then we know that this sum converges to G plus H. This is true by proposition 11.4 on continuous perturbations, and this by definition is equal to our gamma limit F. And so this proves the gamma convergence result, Fn gamma converges to F. Now the second point that we need to show in order to apply theorem 11.2 is the equicursivity of the functions Fn with respect to the strong topology of L2. So we claim that Fn is equicursive in L2 of 0, 1. And let's see the proof of this claim. Okay, so by remark 11.11, so a remark that we just did, we saw that it is sufficient to show the existence of some M in R such that this common sublevel is non-empty and precompact. Okay, if we show that we can find M such that this guy is non-empty and precompact, then by remark 11.11 we conclude that the sequence of functions is equicursive. And now let's just do that. So first of all, notice that I mean, indeed, not that, maybe, first of all. Sorry. So first of all, note that Fn of 0, this is just equal to, I mean, by direct calculation, I mean, by just looking at the definition, this is equal to the integral of arctan of x squared. And the arctan now is less or equal than pi over 2 in absolute value. And therefore, if you square it, this is all less or equal than pi over 2 squared. And I hope that this is less or equal than 10. I mean, but this is not important. We just need an upper bound. So just choose m equals to 10 in the definition of k here, proving that 0 belongs to, proving that 0 belongs to this set, so that this set is non-empty. So we are left to show, so we show that k is non-empty for m equals to 10. Now we want to show that k is also precompact. And but this is actually very easy to show. Maybe we don't do all the calculations, but it's easy to see. So K is precompact. Again, maybe here we have a typo, pre-compact. So indeed, assume that Fn of u is less or equal than 10, then we obtain that by definition, since this is the first term in our functional, and this is the second term in the functional. So by definition of Fn, you obtain, number one, that the derivative of u dot, sorry, the integral of u dot squared is less or equal than 10 over n. And number two, you obtain this inequality here on u minus the arctan of x squared. And I mean, this is telling you that u dot squared is bounded because this is obviously less or equal than 10. And the second inequality instead is telling you that u is bounded in L2. So in total, we obtain that u is bounded in W12 for some constant c, which does not depend on n. So this is important. Okay. Does not depend on n. And sorry, this way. And does not depend on u, of course. Okay, so it's just a constant. And therefore this shows that if u belongs to k, because this is the condition, u belongs to k, then you prove that u belongs to a ball of the W12 norm. So k containing k tilde, where k tilde is this ball of the W12 norm. Now we know that the balls of the W12 norm are compact in L2 thanks to the compact embedding. W12 embeds compactly in L2 of 0, 1. This is true by theorem 7.27. And notice that, so this is true because, basically because this guy here, so this set is bounded in W12, and compact operators bring bounded set into compact sets by definition. And so the image through the embedding, which is just the identity of k tilde in L2, is compact, meaning that this set here is compact in L2. And therefore, by definition, k is pre-compact, since obviously if you have this inequality, this inclusion, then you also have the inclusion for the closure, because this set here is, in particular, this set k tilde is closed, being compact in L2. So in particular, you have that k closure is containing k tilde, and now k tilde is compact, so k closure is closed and containing a compact set, and therefore k bar is closed, showing that k is pre-compact. And so this proves that the sequence Fn is equicursive. Okay, now just as a recap, we have shown that 1, Fn is equicursive in L2, and 2, that Fn gamma converges to F in L2 of 0, 1. And therefore we can just apply theorem 11.12 and conclude that the infimum of the problems over L2 converges to the minimum of the limit functional f over L2. That is, I mean, we define these guys to be the Mn, so we just proved that Mn converges to M, where M is given by this guy here. And now remember the definition of f of u. We have that f of u is equal to, so let's go back to the definition. Yeah, so f of u is this guy here. So it is plus infinity if u is not constant, and it is this quantity if u is constant. So in particular, if you look for a minimum of this problem, you know that the minimum exists because this is a gamma limit, and theorem 11.12 guarantees that gamma limits always have a minimum. then the minimum must be among the functions which are constant. And now and therefore this means that what I wrote here, it means that m, which is this minimum, is just equal to the minimum for lambda in R of this integral here. And now this is just a polynomial of degree 2 in lambda, and therefore you can just compute, if you want, you could actually compute an explicit value for the limit m. Okay, so this concludes the analysis of this example, and I will stop here for the first hour of the lesson.